Section 4.3, Maxima and Minima. In this section, we learn how to find the largest and smallest values of a function. This is useful because we use functions to represent profit or height, and being able to find the largest value of profit can help a company figure out how to maximize their profit. So let's get started. We'll start by talking about absolute extrema. I have a graph here. This is just a typical quadratic function. Looks like it's been shifted up 1 unit. So we're looking at x squared plus 1. And if we take a look at what happens to this function as x increases, so we're watching as x goes towards positive infinity, the values on our curve are increasing. And as x gets bigger and bigger and bigger, this curve just continues all the way up to infinity. So as x goes to infinity, the function value increases to infinity. It just gets larger and larger and larger, almost like there is no stopping point. The same thing happens if we look at x going to negative infinity. The function value increases infinitely to positive infinity. In this case, we would say that there's no absolute maximum for the function we have graphed because there's no such thing as a largest value. We know how infinity works. It's not a number. It's something that's completely growing all the time. It never stops. However, we can find a minimum value. If we zoom in to where x is equal to 0, and then we look at where that hits the function value is 1. So at x equals 0, the function value is 1, but then every other point on this curve is larger than 1. There's not another point that goes lower than 1. So we can see that everything is above that value 1, which means this is the smallest value the function ever takes on. We would say that this function has an absolute minimum, and we're talking about over the entire interval where x gets to go from negative infinity to positive infinity. Within that interval, this function has an absolute minimum because there's no smaller value that this function will put out. Let's look at a formal definition for absolute extrema. So if f is our function, of course it needs to be defined, and we're going to specifically talk about over intervals called I. And we're going to let c be some x value that lives within that interval. To compare that to the picture we have on the screen, the interval I that we were talking about is the interval from negative infinity to positive infinity. C is a value inside of that interval. Now, in this case, the interval includes all real numbers, so it's not very restrictive. But you'll see in some cases we won't use the entire number line as our interval I. But in this case, C is the value that we have our critical point at. Now, the definition we're looking at is for an absolute maximum. And we said we don't have an absolute maximum, and that's true because there's not a single x value c that we could plug into f so that the value is greater than or equal to all other values of our function. Remember, we said that the largest value we could find was infinite, and that's a number that's constantly changing. It's getting bigger and bigger and bigger. So we don't have an absolute max here. Let's compare it to our absolute minimum definition. Again, we're looking on the interval I for this function that we have graphed. Our function f has an absolute minimum on the interval I because we found a value c at x equals 0, such that when we plug 0 into our function, the function value is smaller than all other values that come out of our function. So we call that the absolute minimum on I, and then the absolute extremum, that's the function value. So the minimum happens at c equals 0. But then the extremum, the minimum value, is what happens when you plug that x value, the c equals 0, into your function. We get 1. So the minimum happens at x equals 0, and then the minimum value is the function value, which is equal to 1. Now there's something to note here, that the idea of absolute extrema can sound confusing, but I want to clarify that absolute in this case does not involve absolute value whatsoever. We're saying absolute because it's definite. There's nothing else that is either larger than or smaller than, depending on what we're talking about. So don't confuse this with anything that's involving absolute value. Also, the absolute max or min is specifically over an interval. Now, in this case, our interval was including the entire x-axis from negative infinity to positive infinity, but we won't always include all the values. So if you want to make a claim about an absolute max or min, you always need to specify the interval that you're working on. An extreme value theorem is something that will help us to find these max and min values. Before we get to that, let's talk about how functions can have both absolute maximums and absolute minimums. It can have one or the other, and sometimes it can have neither. On the top left, I have the graph of x cubed. Looking at this function, we can see that it's defined from negative infinity to positive infinity. So the interval we're working on goes from negative infinity to positive infinity. And then looking at our graph, as x gets larger and larger, the function gets larger and larger. So there's no maximum on that side. As x gets smaller and smaller, the function gets smaller and smaller to negative infinity. So this function is an example that has neither extremum. We have no absolute max, no absolute min. Moving on to our next function, this is a graph of a rational function that looks like 1 over x squared plus 1. As x gets larger and larger and larger, we can see that the function approaches the x-axis like an asymptote. And as x gets smaller and smaller and smaller, the same thing happens. So if we try to pick the interval that we're working on, we can see that we're looking at the interval from negative infinity to positive infinity, because our function is defined over that entire interval. And then if we wanted to talk about the maximum value, looking at all the points that make up this white curve, the largest y value happens right here at this bump. That's going to be our maximum value. So our absolute max happens at x equals 0, but then the max value is equal to 1. And for the minimum, we can see that both tails of this graph are approaching the x-axis, which means a y value of 0. But it's never actually equal to 0. So if you think about asymptotes, they get infinitely close, but they don't actually touch. So this curve is getting closer and closer and closer to the x-axis, but it's never equal to 0, which means there's always going to be another real number between the value you're looking at and 0. There's no absolute min here. And that's a little bit counterintuitive. Looking at this graph, you might say, oh, the minimum is 0, but this function is never equal to 0. It gets close to it, but it's never equal to it. Moving on to our next graph, we have the graph of cosine x. This graph oscillates back and forth between 1 and negative 1. We can see that there are hilltops. This is where maximum values would occur at hilltops, and we can see that there's some valleys. So looking at the domain for cosine x, we would pick the interval, again, negative infinity to infinity. We can see that the maximum value occurs multiple times. So the max value occurs at multiples of 2 pi. And the max value of cosine x is equal to 1. So we have our absolute max at x equals multiples of 2 pi. And then the max value is equal to 1. And then for the minimum, we have almost the exact same thing. So our minimum is happening at multiples of pi plus 2 pi n, essentially. And the minimum value is at negative 1. So we have our maxes at the top and our mins at the bottom. So when we're looking at extremums, we're looking at the function value. If we're looking at where they happen, then we're looking at the input, the x value. Let's move down to the 3 graphs on the bottom. Notice that these are either piecewise functions or truncated functions. Unlike the 3 functions we just talked about, the interval I is not going to be the entire x-axis. So on the bottom left, we're looking at a piecewise function, and it specifically goes between x equals 0 and x equals 4. So the interval that we're looking at goes from, and it's a closed interval here, we have from 0 to 4 on the x-axis. I know it's a closed interval because I have my circles filled in at those left and right endpoints. If I wanted to pick a maximum value, I would just look for the largest y value for any of the points on the graph. And that looks like right here at 2. So our max occurs at x equals 0, and the max value is 2. The minimum, if I wanted to pick a minimum on this graph, I would actually have some trouble. Intuitively, you would want to say it's at -2 because the lowest part of the graph dips down to -2. However, the function is not equal to -2 ever. It gets very close to -2, but it never lands on the actual value of -2, which means it doesn't have a minimum value. And this is just like the graph up here with no minimum value because it's asymptotic, and this one has an open circle. So the function values are approaching something that looks like a minimum value, but it never reaches that value. Moving on to our next graph, we have another truncated parabola. The interval that we're working on here starts at x equals 1 and goes all the way up to x equals 4. And within this graph, we're able to identify an absolute max and an absolute min. Absolute max happens over here at this closed point. It occurs at x equals 4, and the max value is equal to 4, the y value. As far as a minimum, we would not pick this other endpoint. That's not a minimum value. Instead, we would pick this point right here at the valley of our graph. It happens at x equals 2. And our min value, the y value at that point on the graph, is 0. So our minimum value is 0. All right, we have one more to look at. Now looking at this graph, we can see a closed circle at x equals 0. So we know our interval starts off at x equals 0. However, we don't see what's happening at x equals 2. It actually is approaching an asymptote, a vertical asymptote. So we're not going to plug 2 into our function, but we're going to let our inputs get very close to 2. So we're going to use a round bracket on that interval to make sure and note that we're not plugging 2 into our function. The function's not defined at 2. Looking at this graph, if we wanted to pick a single point that represents the maximum value of our function, we're not able to because this function heads all the way up to infinity. And if we wanted to talk about a minimum value, we would be able to pick that because we have a closed point down at the bottom where x is equal to 0. So we have a min that occurs at x equals 0, and our min value is equal to 0. The function value at that lowest point is equal to 0. Theorem 4.1 from this section is called the extreme value theorem. It basically says that for a function f, let's assume we're talking about a continuous function over a closed bounded interval. This theorem says that there has to be a point on that closed interval where f has an absolute maximum and an absolute minimum. And that's a lot like the middle example on the bottom row. We're looking at a closed interval and continuous function. We had both a maximum and a minimum value for this function. So an extreme value theorem is talking about absolute extrema on a closed interval. It guarantees that you will have both a maximum and a minimum. Let's talk about locating local extrema and critical points. A local maximum for a function is something that exists on an open interval so that within that interval it looks like you have a maximum. We've got a graph here, and it's just kind of a rough sketch, but taking a look, if I were to make an interval around these red dashed lines and tell you to only look within that interval, you would likely say that this hilltop is a maximum. But if I allowed you to move the right boundary so that it went to the other side of this peak, you wouldn't call it the maximum anymore, because this peak is also a max, and it's more of a max than the lower peak. But with a local extrema, it just says that you can find an open interval so that in that open interval, it looks like a max. So we don't need to consider every interval, we just need to find some open interval and then look for the critical points inside of that interval. Same thing for a minimum. We would find an interval so that there's a point within that interval that puts our function at a low value compared to everything else inside of the interval. Now looking at this function, we would say there is no absolute minimum because the function continues in a downward trajectory to negative infinity, and it keeps going. But it does have a local minimum at this little valley because we can find a small interval around that. That so long as we look within that interval, this open interval, we can say, oh, this point's lower than all of the other function values in that window. Something to note is that if you find an absolute extremum, it's also technically a local extremum, except when it occurs at an endpoint. So if your absolute max or your absolute min comes from that closed interval, then we don't call that a local extremum, we call that an endpoint extremum. Fermat's theorem. To talk about Fermat's theorem, we first need to talk about what a critical point is. A critical point is the location of these extrema, and a critical point is definitely going to occur where you have a derivative that's equal to 0 or a derivative that is undefined. And that's because if we're looking at a max or a min, we know that a zero derivative will find us those maximum and minimum values. So first we have to understand the critical point is the point that gives you these maxes or these mins. Fermat's theorem says that f has a local extremum at these critical points. If you know that there's a local extremum, then you can guarantee that the derivative is zero there. Now it's really easy to read this backwards. A lot of times we read this as if the derivative is zero, you're guaranteed to have a local extremum, but that's not what this says. It says the reverse. If you know that there's a local extremum, then I can guarantee you that the derivative is equal to zero at that point. To prove this theorem, we're going to suppose that a function has a local extremum and that it's differentiable, just like the theorem says. And we're going to show that the derivative at that c value has to be equal to zero. To do this, we're going to show that the derivative at c is greater than or equal to zero, and the derivative at c is less than or equal to zero. The only way for our derivative at c to be both greater than or equal to zero and less than or equal to zero is if it's actually equal to zero. So our goal is to show that those derivatives are equal to zero, just like the theorem says. So we'll start off by supposing that the local extremum that we assume f has is a maximum. Now we could do this with a minimum, but we're going to do this with a maximum. You can do it on your own if you'd like with a minimum. So we're going to suppose that we have a maximum at x equals c. If that's true, then our function at c has to be larger than our function everywhere else within the interval I. So that's from the definition of a local extremum, and the interval I is that open interval around c. We're also supposing that f is differentiable, so if it is differentiable, then the derivative at c has to exist. This is just our limit definition of the derivative. Notice that this limit definition of a derivative, as we learned last chapter, this is a two-sided limit. X is approaching c from the left and the right. So since this limit exists, we know that the left and the right-sided limits exist. So we have the left-sided limit over here, where x is approaching c from the left. So if we're thinking about a number line, c is on that number line, x is approaching it from the left. And then we have a right-sided limit, where x is approaching c from the right. So if we had our number line with c on it, x is coming from the right. For each one of these limits, we're going to make a substitution in the numerator. So our numerator in both cases is f of x minus f of c. And we happen to know something about how those two numbers relate to each other. At the top of the right screen, we have the inequality f of c is greater than or equal to f of x. We can subtract f of c from both sides and see that we have that f of x minus f of c is less than or equal to 0. So we know that we're dealing with a negative number when we look at f of x minus f of c. So if we're looking at the left-sided limit, for example, we know that we're looking at the limit where x is approaching c from the left. That numerator is some negative number. The denominator is x minus c. If x is coming from the left, then x is smaller than c. So if I take a small number and I subtract a larger number, I get another negative number. So if I have a negative number divided by a negative number, I'm going to get a positive number. for this limit. So looking at the left side, we see that f prime at c is equal to some positive number, or 0. In other words, we have the derivative at c is greater than or equal to 0. We're going to use the same kind of logic for the right-sided limit. This time x is approaching c from the right, meaning x is a larger number than c. So our right-sided limit, where x is approaching c from the right, the numerator is still some negative number, but the denominator, this time x minus c, that's going to give us some positive number. A negative divided by a positive is a negative, so this is telling us that the derivative at c is equal to some negative, or 0. Which means we've shown that our derivative is both greater than or equal to 0, as well as less than or equal to 0 at the same time. The only way for those inequalities to both be true is if our derivative at c is equal to 0. Let's practice using Fermat's theorem. Now remember that this theorem does not claim that a function must have a local extremum at a critical point. Instead, it just states that critical points are the candidates for local extrema. So looking at the variety of graphs we have here, in the first graph, graph A, we see that there is a critical point right above the value c. We have a derivative that's equal to 0. We have the tangent line graphed there. And we can clearly see that this is a local maximum. Moving on to the graph B, right above the value c, we can see that we have a corner on our blue graph, which creates a vertical tangent line. And at that vertical tangent line, the derivative is undefined. So either the derivative is 0 or undefined. Fermat's theorem tells us that we should investigate to see if there's a max or a min there. And looking at this graph, we can see that there is a maximum right at the top of that corner, local max. Moving on to graph C, we can see that we have another corner right here above C. The derivative is undefined, so we can't even graph the tangent line here because it doesn't exist, but we can see that there is a minimum value that occurs at that corner. So the top 3 cases are all like best case scenario. You have a critical point and you're able to locate a maximum or a minimum at those critical points. Moving down to the bottom half of the screen, graphs D and E, we have critical points, but no local extremum at those critical points. So at graph D, we can follow above x equals c and see that we're able to find a horizontal tangent line there. So we do have a 0 derivative at c. However, this is not a max or a min. We'll learn later that this is something called an inflection point. And then looking at graph E, we have another situation where we find a critical point at x equals c. We do see that our derivative is undefined at this point. However, it's not corresponding to a max or a min. So when we think about Fermat's theorem in this case, we need to remember that the critical points that come from a derivative equal to 0 or a derivative that's undefined, those are just potential candidates for extremum. They are not guaranteed to find extremum, but it helps us narrow down where we're going to look. I'm going to end this video before it gets too long. Check in for the next one that shows you exactly how to find these critical points mathematically.